Hi everyone, this is a tutorial on hypothesis testing of a population mean when we have a single population and hypothesis testing of a population proportion. So I'm just going to work a couple of quick examples just to demonstrate how we do a hypothesis test for these two various situations. Before I do that, I just want to quickly refresh your memory on the key steps in a hypothesis test. So I'm going to switch over to my handy dandy iPad to do just that. Okay. So you may recall that we talked about 5 key steps in a hypothesis test. The first step is to state the hypotheses. So step 1, we have hypotheses. And there are 2 hypotheses. One is called a null hypothesis, which we denote by HO, and the other one is called an alternate hypothesis. So we could be testing for mu, or we could be testing for a proportion, right? And then of course we could be testing that the mean is greater than, the mean is less than or equal to some value, in which case the less than some value, in which case the null would be it is greater than or equal to that value. Or we could be testing the mean, HOHA, is greater than a particular value, in which case the null, which is the opposite, would be the mean is less than or equal to that value. Or we could be testing that the mean is not equal to a particular value, and therefore the null hypothesis would be that it is equal to that value. So what we notice is that the null hypothesis is always opposite to the research hypothesis. We do the same thing over here. We could be testing that the population proportion is less than some value, in which case the null hypothesis would assume that it is greater than or equal to that value. Or HOHA, the proportion is greater than a particular value, in which case we would assume in the null hypothesis that it is less than or equal to that value. And finally, HOHA, that the population proportion is not equal to a particular value, and so therefore we will assume in the null hypothesis that it is equal to that value. So just reiterating that the null hypothesis and the alternate hypothesis have to be opposites to each other. So that's step 1. Step 2, we have to measure the evidence that we're going to collect to support our research hypothesis. We're not trying to support the null hypothesis, the research hypothesis, which is HA. And we either find enough evidence to support it, or we don't find enough evidence to support it. So step 2 would be our test statistic, which is how we measure the evidence. And we measure the evidence by looking at the sampling error and asking how many standard deviations is that sampling error away from the mean. Because remember, when we take a sample, it is an estimate of the population parameter. So if I'm testing a hypothesis about a population parameter, I'll take a sample, look at the sample, and ask, is that sample representative of that population? Well, how could I tell? I will look at how far that sample is from the population value that I am sort of hypothesizing. And if the sampling error is very large, then it means that the sample is very different from the population. If it is small, it is not different. So we will have to determine at what point that the sampling error is sufficiently large that we will reject the null hypothesis, all right? But we need a measuring device, and that measuring device is really a Z or a T, standard deviations, right? So for population mean, if we're testing a population mean and we know the population standard deviation, then it would be our sample minus our population mean. So that's a sampling error. Sigma over the square root of n. That's when sigma is known, or T, x bar minus mu, s over root n when sigma is not known. And we have degrees of freedom, n minus 1. For proportion, it would be the standard normal, which would be p bar, our sample value, minus p, so that gives us our sampling error, and then we divide by the standard error of the sample proportion, p times 1 minus p over n, okay? So that's the test statistics. And we recall when we did the empirical rule and outliers, we talked about large values of z or t represents outliers, right? I think we started talking about 3 standard deviations represented an outlier. But for our hypothesis testing, less than that might actually be sufficient to consider it an outlier. The other thing that we need is a decision rule. And what the decision rule will allow us to do is to determine at what point the evidence is strong enough. In other words, at what point that sampling error is sufficiently large. And remember, the sampling error is going to be measured in terms of Z or T. So we will need to create a rejection region. If it's a right tail test, then this would be alpha, whatever that is. In most cases, we've been doing 5%. And our rejection region would be here. This is where we reject the null hypothesis. If it is a left tail test, then we simply have this situation where our rejection region will be in the left tail of the distribution. This would be alpha, and this would be our critical value, Z or T. And we will reject the null hypothesis if the test statistic falls in that region. And then, of course, if we are doing a two-tailed test, then we are not interested in proving either the population parameter is greater than a value or less than a value. We simply are trying to prove that it is not equal to a particular value, in which case the evidence can be found in both tails of the distribution. So an outlier in the left tail or an outlier in the right tail would be sufficient evidence to support us. But because we want to restrict the total size of the rejection region to alpha, alpha being the significance level or the significance of the test, then we will have to divide it into 2. So alpha over 2 in this tail, alpha over 2 in this tail. All right? And that will help us set up the rejection regions. The significance level, you will recall from by definition, is the risk of committing type 1 error. In other words, rejecting the null hypothesis when it is true. So if we want to restrict the risk of committing type 1 error to alpha, we must make the size of the rejection region alpha. Right? So if alpha is 5%, we say we don't want more than a 5% chance of rejecting the null hypothesis when it is true. The reason why we make the rejection region the size of alpha is because that is the only place that you will potentially commit type 1 error, is in the rejection region. right? Because remember, the definition is rejecting the null when it is true. So it means that before you could commit type 1 error, you must reject the null. All right? And where do we reject the null? In those yellow spaces that I'm showing you right here. That's where we reject the null. So if you want to restrict your risk of type 1 error to 5%, you must restrict the size of the yellow regions to 5%. Okay? Cool. And that's step 3. Step 4 and 5 are just the analysis and the decision and conclusion. So step 4 will be our analysis. And step 5, the decision and the conclusion. So always remember this. Your decision is whether or not you're going to reject the null hypothesis. That's your decision. And that is based on your decision rule, because your decision rule tells you when to reject it. So after you've done the analysis and you have the data, is it sufficient to reject the null hypothesis? All right. So typically our decision is based on this idea that if our test statistic exceeds, right? So if the absolute value of the test statistic exceeds the critical value, Z critical, right? The absolute value of the critical, all right? Or if p-value is less than alpha, we'll reject the null hypothesis. Otherwise, you fail to reject it. Or if t is greater than or equal to the absolute value of t critical. All right? So I use absolute value because I don't want to have to write it if your critical value is a negative value, if your critical value is a positive value. So just using the absolute values would suffice in this case. If we compare the critical value to the value of the test statistic, we call that a critical value approach. If we compare the p-value to alpha, then we call it the p-value approach. And what is p-value? Just to refresh your memory, the p-value is the probability of observing the sample that we observed, or samples that are even stronger than it, if the null hypothesis is true, right? And of course, we're looking for small probabilities in order to reject the null hypothesis. So just to kind of understand the logic in that, if I said that the mean of a value is 500, right? The mean, it could be whatever it is, the mean of a variable. So say I spend $500 on gasoline per week on average, but I believe that the price has gone up. The average price, the average expenditure on gasoline has gone up. So if I get a random sample with an average, sample average of $600, the logical question is, if the true mean is 500, what's the chance of me getting $600 average, or $600 average? If the chance of that is very small, then you have to conclude, assuming that your sample was properly taken, that the average price of gasoline or expenditure on gasoline in a week has gone up. Not a week, maybe you could say a month. 600 a week would be a lot, but maybe 600 per month if you're doing a fair amount of commuting, right? So that's how you would compare your values. The p-value, if it's very small, is because you have a very large sampling error. All right, and then your decision is, as a matter of decision, your conclusion is that you either have support for your research hypothesis or you don't have support for your research hypothesis. So those are the 5 key steps. All right. Now let's look at an example. So in Brightspace, I have this particular file which has these problems right here, and so I'm going to work one of these problems here, and then the next one would be your problem to work. So we'll do 980 and then you will do 981. And then I'll do 983, which is a proportion question, and then you'll do 984. All right? So here goes. Fairfield Automotive is the local dealership selling Honda automobiles. It recently stated in an advertisement that Honda owners average more than 85,000 miles before trading in or selling their Hondas. To test this, an independent agency selected a simple random sample of 100 Hondas and who had either traded or Honda owners, who had either traded or sold their cars and determined the number of miles on the car when it was actually traded in or sold. Excuse me. It plans to test the Fairfield's claim at a 5% level. State that an alternate hypothesis. If the sample mean is 86,200 miles, with a standard deviation of 12,000 miles, what conclusion can be reached about the particular claim? All right. So remember that what is Honda claiming? That they trade in at more than 85,000 miles. Okay. So we're going to try to find evidence to support that. So here's what we do. Step 1, our hypothesis. We were asked. I'm going to do the 5-step so that way you actually can see it progress. HO, HA. So average upon trading or sale is greater than 5,000. That's what we want to prove. So the opposite to that, it will be that it is not greater than 85,000. So average mileage, I'm missing an A here, upon sale or trading would be less than, okay, let me just put that in symbols, less than or equal to 85,000. And so the average mileage upon sale or trading is greater than 85,000. Putting that in symbols now, since we're testing for mean, we would say mu is greater than 85,000 is our research hypothesis. The opposite of that is it is less than or equal to 85,000. So that's step 1. Step 2. So the test statistic. So this problem involves hypothesis testing of a mean, population mean, single sample. So therefore, we are interested in the sampling distribution of a sample mean to measure our evidence. We don't know the population standard deviation, so therefore, we will measure the evidence in standard deviations using the t distribution. X bar minus mu s, not sigma, but s, over root n with degrees of freedom n minus 1. Okay, that's our test statistic. 3, our decision rule. So our sampling distribution is a t distribution, so it looks like this. It is symmetrical, as you know, for the t distribution. And is this a left tail or right tail test? It is a right tail test. We are looking for evidence in the right tail of the distribution. And so this is 0. And this is just a one-tailed test. So here is our rejection region, reject HO. And then of course this region right here is we fail to reject HO. All right? And remember, the size of the rejection region is alpha, 0.05. So what is our critical value? It's not Z, sorry, it's actually T. T critical for one-tailed test would be T with 5% in the tail. What's our degrees of freedom? Our degrees of freedom is 79 because we have 80 as our sample size. So n is equal to 80, just make a note. n is equal to 80. Degrees of freedom is equal to 80 minus 179. It turns out that that critical value is actually 1.664. 1.664. In case you don't remember how to use your t-distribution, we will go to the t-distribution, look up 5% in the tail, 79 degrees of freedom. So let's take a look at that. Here's the t-distribution right here. No, sorry, that's the normal distribution. Here's the t-distribution right here. So we can see the area in the tail. So we want to look under the 5%. And then where's the degrees of freedom? 79. And so therefore 1.664 is our critical value. That tells us when the sampling error is sufficiently large that we could reject the null hypothesis. So if our t-value is greater than or equal to 1.664, we will reject the null hypothesis. So that's the critical value approach. The p-value approach would be if the p-value is less than alpha. Always, that's always the decision rule. Or if the p-value is less than alpha, we reject HO. And that's always the rule. So we could always convert the value of our test statistic to a probability. See, what is the probability associated with that? And that sort of uses the material from chapter 7, where we found probabilities of sampling distributions. So step 4 and 5 now. Steps 4, analysis, would be t is equal to, this is the data that we have. The sample mean was 86,200. The population mean that we assume is 85,000. And then the standard deviation was 12,000. And we got to divide by the square root of 80. All right? Make sure I'm doing the right thing. Yes, and the answer is that this is 0.8944. 0.8944, as you can see, is not greater than 1.664. But let's find a p-value. The p-value, how do we find it? What we will look for in the table is what is the area in the tail associated with this t-value when the degrees of freedom is 79, the same 79 that we used earlier. So let's go back to our table. 79 degrees of freedom, as you can see here. And we're looking for 0.8944. Well, this is 0.846, 1.292, which means that 0.8944 is in between those two values. It is in between here, which means that the probability in the tail, or the area in the tail, will be between 20% and 10%. If I just sort of roll that up here. All right? So it will be between 10 and 20%. That's how you do that. So it is greater than 10%, but it is less than 20%. That's our p-value. And because we just have a one-tailed test, the area in the tail that we get is the p-value. If we had a two-tailed test, we would have to multiply that area by 2, because the table will just give you the area in one tail. But when it's a two-tailed test, we have to consider that the evidence can be in both tails. So we multiply that value by 2 to give us the p-value. In other words, one tail only gives you half of the p-value. But that is only for a two-tailed test. This is a one-tailed test. All right, so that's step 4. We have the p-value and we have the value of our test statistics. So step 5 can be written as this: our decision and our conclusion. So since That's our decision now. Since 0.8944 is actually smaller than 1.664, that's if we're using the critical value approach. Or since the p-value is actually greater than 5%, and we could tell by looking at the range here. We said it's between 10 and 20%. If it's between 10 and 20%, it is greater than 5%. We fail to reject HO, the null hypothesis. What's our conclusion then? We have insufficient evidence that the trading average mileage is greater than 85,000. We have insufficient evidence the average trading or sale mileage exceeds 85,000 miles. And so, excuse me, can we commit an error? Yes. In this case, it is the possibility of type 2 error. Okay? So that's the basically the long and short of this particular problem right here. I've given you the full 5 steps. The second question, part B of that question, I should say, the second part of that question, I really ask you for the 5 steps. So what conclusion would you draw? And you go through the process of the hypothesis test. And here it is. We don't have evidence to support the claim of the Honda dealer. Okay, so that's an example involving hypothesis test of the mean. There is a question that you can do, which is the second one here. I will leave that question for you to do, so you could sort of pause the video and then try that question. So we have Sanchez Electronics sells electronic components for car stereos. It claims that the average life of a component is 4,000 hours. The test is claimed it has selected a random sample of 12 components and traced the life between installation and failure. So we have a sample of 12, and then we say state the appropriate hypotheses then, and then assume that we want to conduct a test at 5%. What conclusion can be reached about the life of those components and so forth? So what are they claiming? They're saying that it exceeds 4,000 hours. Right? So for this question, you're going to have to calculate the sample mean and the sample standard deviation. You know the size is 12. Use Excel to help you find that. Don't do that by hand. And then Excel should give you the values that you need. So I want you to pause the video and actually go ahead and work that problem. After you've worked that problem, compare your answer with my answer. All right? So I'm going to give you excuse me, the information on this in terms of what the answer for this actually looks like. So for this particular question then, if you were doing this, you would have the following. I'm going to do it very quickly, but this is what you should end up with. HO, HA, we're trying to prove that the component life exceeds 4,000 hours. So therefore, it does not exceed 4,000 hours. 2, the test statistic, because we don't know the population standard deviation, it will be T is equal to X bar minus mu S over the square root of n. 3, the decision rule. So it is a right tail test according to our question, and so therefore this would be alpha 0.05. Our critical value would be T critical is equal to T 0.05, but we only have a sample size of 12, and so therefore 11 degrees of freedom minus. So it's remember it's n minus 1, and that turns out to be the critical value is 1.796. By now you should know how to go and find that. And so if our t value is greater than or equal to 1.796, we will reject the null hypothesis. You know, the p-value approach says is that if the p-value is less than alpha, we will reject the null hypothesis. When you do your analysis now, step 4, so t will be equal to the average you will get for the data is 4366 minus 4000, and the standard deviation that you will get for that data is 1000.85 hours divided by the square root of 12. This turns out to be 1.266. It's not enough, as you can see, 1.266. The p-value, when we go to the table, remember you're going to now look under 11 degrees of freedom, and you're going to look for 1.266. You will find that the p-value is greater than 10%, less than 20%. Right? We actually have the same p-value as the last question, but it's not. But remember that you have to use the 1.266 to try to find that p-value, 11 degrees of freedom. Step 5 then is that this is our decision, and our conclusion is we have insufficient evidence. Sorry, before I could, that's my conclusion. I'm supposed to make my decision. First, since 1.266 is less than 1.796, that's the critical value approach, we fail to reject HL. If you're doing p-value approach, then you simply say that the p-value is greater than alpha, and so therefore we fail to reject null hypothesis. What's our conclusion? Insufficient evidence. We have insufficient evidence, okay? The components of the component life exceeds 4,000 hours. So, since we did not reject the null hypothesis, can we commit an error? The answer is yes. Possibility of type 2 error. Okay. But there we go. So you should have hopefully gotten that as your answer. And if you didn't, well, study this example again and try it over again, and then come back and make sure that you get this answer. So that is the second example involving the hypothesis test of a population mean for a single population. All right, I'm going to stop the video there, and I'll do part 2 and do the questions on proportion in a separate video in the next video. So part 2 to this will be on proportions. It just makes it a little easier to divide it into 2 smaller videos than 1 long one. So I'm going to stop right here. Go to part 2 for proportion.